So I'm Richard McDougall, and I wanted to today talk about just what's going on in the software-defined storage industry, and look forward to how the hardware and the software is changing and the apps that we're going to see in the future on that. So in this talk, I want to talk basically about these three areas. So basically today I want to cover what's going on with the hardware space, and I want to talk about what's going on in the container and open storage industry. And then a lot of the solutions here on the right-hand side, there is a lot of software-defined storage solutions, both proprietary and open source. So talk about sort of where they fit and why they're different and what sort of problems they solve. So to try and rationalize this, I put together this chart and to try and think about there's a lot of different applications, there's a lot of different solutions, and actually there's some petitioning about how these map together. So on this chart, this is the capacity of the storage on the horizontal axis. So we can see going from small storage, like tens of terabytes, and up to the super high capacity petabyte scale storages like the HDFS and others. And then on the y-axis, we've got the IOPS. And so is this app something that runs in a VM and does 1,000 IOPS like most of the databases we see? Or is it the super high-end databases that are starting to emerge now, like Cassandras or HANAs or Vaults or those others that are either in memory or super high performance and need extreme amounts of IOPS. And then in the top right, we've got a few new things emerging which are sort of a hybrid between the both of them. So Scality is a scale-out storage solution, and HBase is a key value store, but you can also scale to extremely large amounts of data. So those kind of sit in the middle where they're doing a lot of random I/O, a lot of IOPS, but they still have high capacity as well. So most of the VMs we care about today are here. So you can see the databases, the exchange servers, all the things that store data. And they really are just usually hundreds or low thousands of IOPS. But the difference is we consolidate them. So we might have 100 of those running or 1,000 of those running. And so therefore we need storage that can do 1 million IOPS at the back end because we're running a lot of them on the system. But there's all these new workloads. And I want to cover a little bit about what they are and why they're different, because somehow we have to start to cater for all of these as well. And as the storage hardware and software emerges, there are different solutions that cater really well for these and some new challenges that come in as well. So let's have a look. So I guess the other thing that's going on at the same time is, so we've got cloud-native applications emerging. And so this is a term that's being used largely as the way that we run and manage a lot of those new applications. So a lot of the times, the new application space has these new fancy databases and Cassandras and other things, MongoDB that goes with it. But there's a different way of managing those that's emerging as well, which is important because the main thing that comes out of this is cloud-native applications are developer-driven. So there are APIs so the developers can say, I want an instance of MongoDB and I want to have this capacity and this performance. And it shows up as a service. You don't know where it's installed, how it's configured, and then you want to attach your application to that. And so these applications are often deployed with containers, sometimes in VM, sometimes containers. There's another whole set of talks here at VMworld that go into that topic. And the main thing here is that these are showing up as data services underneath. So when you see MongoDB or Cassandra or even a MySQL instance, they're data services that are attached to these applications and exposed through containers. So at the end of this talk, I'm going to come back to well, how do we run all these services on the storage architecture? And now just talk a little bit about, well, the containers themselves. We know how VMs work. We know what the requirements of VMs are. They have VMDKs underneath them. But what do containers need for storage? So containers are basically little Linux instances. You can do this on Windows now as well. And those are, the storage for containers sort of takes two forms. One is the backing storage for the bootable file system for a container, and the other is where does it store its data? Like if I'm MySQL, I need to boot off of something, but I also need to have somewhere to store my MySQL data files. And so the boot environments are created with this property that you can create them very rapidly and tear them down. They're meant to be stateless. And so with Docker, for example, you end up with stateless runtime environments by virtue of some sort of technology to take copies of the root file system, create your new environment, stack all the pieces you need inside of it, often through a layered file system, and then let that thing boot. And then when you turn it off, it all goes away again. And so the properties, the way this is done natively is, in its most simple form, when this first happened, was Linux would copy its whole root directory or a new root directory for a container and then copy the bits into it it needs and boot it. And that's obviously very slow and very space inefficient. So now what Linux does is use a combination of different things. This is one way that was done right at the start, which is using layered file systems. So you can take a root file system and then you can clone it, and then you have a new root file system that you can read and write into, and then boot that. Modifications to that become local, and you can see through this layering of file systems, they had a way of separating out the modifications, kind of like what we do with redo logs on VMDK, so we can snapshot a VMDK. Union file system wasn't a great implementation, but there are others like device mapper, and there are a couple of other options inside of Docker to do this today as well. But the bottom line is containers need file systems, not block devices, and they need snapshots and clones, and we want to do that really rapidly, and the scale that they need to do that at is much higher. So when we think about VMs and VMDKs, if we think about containers, we typically are talking about an order, maybe 2 orders of magnitude more of these on a system, because the containers are very small, and they need to boot very quickly. And every container might actually stack, maybe like this diagram, might stack 20 layers together. So you can end up with an order of 1,000 times more of these little snapshots required. So there's some benchmarks out there, and they show that the order of magnitude of what you need to be able to achieve. They show 1,000 containers getting created, provisioned, booted, and then shut down again within a minute. And so that's the order of magnitude of provisioning speed that's needed. So that's a little beyond what's in the stacks today. But there are a few emerging file systems and other technologies that are starting to address this. So I'll go a little bit further. So the main summary here is with Linux containers, there are 2 things required. One is this non-persistent boot environment that we just talked through, and there we need a file system with very fast snapshots and clones. And then we need somewhere to put the persistent data. So the persistent data piece is not catered for in the standard container environments. I didn't say this, but the bottom part is reasonably well catered for in the sense that there are Linux file systems that do snapshot and clone, and there's some other things like ZFS and Btrfs that are being used now to do that clone technology. So those sit on top of VMDK. I can clone 1,000 containers. But the right-hand side, where persistent data goes, if you create a container that has MySQL in it, where does the database go? Like, that's persistent data, so you can't just tear that down and throw it away after you shut the container down. So there are a variety of solutions starting to emerge in that space, and it's really critical. Like the default of Docker, for example, is stored on the local disk, and that means if you turn the machine off or the machine catches fire, you've lost your database. And that's not what we expect from databases. So these solutions are figuring out how do I make that reliable so I can move the container if I need to another host, and so that's highly available so that if that goes down, then I've got somewhere else to run the database without having to use upper-level database replication technologies. So there are a few things in that space. Flocker is using some lineage from ZFS to do this replication. And we're actually doing some work right now with vSAN. So we have implementation of this working where Docker will automatically provision the persistent volumes on top of a vSAN volume, and then by default, then that's replicated across the cluster. So all of a sudden it becomes reliable, you can move your container around, you get resilience. And that's a great addition to that solution. So that's the Docker integration work that you'll see coming out of VMware, and then other solutions fitting into this space as well. So this basically summarizes that we end up with this need for the boot environments. We want to put containers on some sort of storage platform for persistent data. So there's a need for shared data as well. In some cases, very rarely, but sometimes you want a shared file system. And some of the shared file systems like Gluster and others are starting to show up in this space as a new way of being able to provide distributed shared file systems underneath. And then, of course, the last bit is, well, there's usually an object store or something else that is needed to store. If you're going to put things like pictures and photos, whatever else, that's a REST API call into another service, and it's an object store. If you're out in a cloud platform, they may have one, but if you're inside the enterprise, this is a growing requirement we see now, running some sort of service on top of your servers that provides an object storage platform that the developers can then code to. So yet another thing we've got to run in our system. We'll get back to this, but more services we need to be able to run, which are storage services, and how to manage those. And finally, just as we cover those new apps and containers, there's a lot of use of these big data platforms in the cloud and inside the enterprise as well. And typically, we see those in silos. And so Hadoop's a classic one. We see a lot of Hadoop usage. I've personally spent a lot of time in the Hadoop space over the last few years, and it's typically set up as a very separate silo, and those are Hadoop machines, and they run just Hadoop and their own Hadoop file system, and then there's not really block storage there, so you can't go and grab your MySQL or your Oracle and run it in that platform. So this is where we want to get to, and at the end of the talk, we'll see how we can actually converge some of the technologies to get to this point. We want to create a common platform. We have some customers already doing this today, and that is basically to say we'll separate out the runtime of these big data platforms from the storage engines. If you can do that, then you can have a common host underneath, so the same storage devices, there will be servers with storage in them, some sort of distributed storage platform that manages those servers, and then on top of that, you want to have a file system representation for Hadoop, and Cassandra and others use that as well. You want to have a POSIX file system for the things that need to do strict POSIX requirements. Hadoop has a file system, but you can't do things like randomly write to a file. So in some cases, you need true POSIX if your application wants to manipulate data that way. And then some block storage for the good old things that still need to just run on block storage, like either the boot images or MySQL database, an Oracle instance, whatever else it is. And then on top of that, something that allocates and provisions all those solutions on top of it. If you do that, then basically you can have one platform. You can say, here's my big data environment. It'll still be probably different from your regular environment because it's got 100x the bandwidth requirements on the network and the storage than anything else does. But this way, at least you can consolidate. You know, you can spin up and provision any shape of big data environment you need without having to think about, well, there's a bit of Cassandra over there and there's a bit of Hadoop over here or something else. So consolidate all into one platform. We can do this today with vSAN, and you can do it with a number of other approaches as well. So that's the applications. Now I want to spin back to like what's happening underneath on the hardware and software front. And so we're going to cover that a little bit, and then we're going to come back and talk about, well, how do I converge all these things together on the same platform? So we think about the original positioning of the applications. The left-hand side would be our traditional applications, and we've got a bunch of new things emerging on the top left-hand corner. So these are our all-flash or hybrid flash, very high I/O rates now. We're seeing like devices that have millions of IOPS in the storage platform. And you can see a lot of those, these are the hardware solutions in that space, Pure Storage, Extreme I/O, SolidFire. Those are all oriented at the top left towards very high IOPS. And then on the top right-hand side, we've got some new contenders which are very different. Like, so the DSSD box that EMC is shipping now is a very high IOPS box. So it does only 10 million IOPS, but it also does very high bandwidth. And so the type of bandwidth that device can do is in the hundreds of gigabytes per second. And the solutions on the left are typically in the sort of 1 gigabyte per second range. So we're talking about something that has Hadoop level of bandwidth. Hadoop clusters are typically like 50 plus gigabytes a second, but also very high IOPS, and it's all flash. So it's a very unique box that delivers a mixture of both. And then the bottom, we see Isilon. So Isilon is a scale-out storage solution, as an example from EMC, has scale-out, so you can add many nodes to it. But that's typically, it's file-oriented, it's designed for very large capacities, and it has high bandwidth. So as you add more nodes, you get more data bandwidth. And so I've observed those systems to be in sort of 50 gigabytes per second range. So very high bandwidths and oriented towards Hadoop and those types of systems. So that's a rough spread of where the hardware is. And really, the reason for most of those all-flash systems is because we're consolidating and increasing performance. And so we've got a bunch of applications we're running. We want to really have low latencies, super low latencies, so we can speed things up. We can take our database unmodified, put it on super low latencies, get the disk response times down to fractions of milliseconds, and then get high performance. So, okay, so that's the hardware technologies. Just to contrast, because we're going to go into like, well, this is a software-defined storage talk. So what is software-defined storage and what does it sit on, and what does the server industry look like that it's going to take advantage of? And you'll see that it's overlapping those capabilities in many spaces. But let's just look at, so there's a pretty big change in the landscape going on in server storage hardware, because now we're talking about industry-standard hardware that has storage devices in it. So we've got disks and flash and other new technologies. So what do they look like? And I realized coming here, like I normalized this because I talk about this from a US point of view. This is the time it's a normalized magnetic storage, like a disco that takes 10 milliseconds, as the time it takes to get from California to Australia. Of course, we're not in California, we're in Spain. But just as a relationship between the various entities, you can see magnetic storage, 10 milliseconds, doesn't really get much better than that. And we'll talk about how that's changing in the future. Slower than that is object storage, sort of hundreds of milliseconds away, typically. And then a variety of different technologies above it. And you'll notice some introductions of some new technologies. These are not replacing the old technologies. These are an insertion in the memory hierarchy for storage. And you'll see the storage stacks either having to, or some of them already getting more sophisticated to take advantage of these. So I'm going to go into a little bit more detail on the next couple of slides, but capacity-oriented SSDs come first. Those are the flash that's been optimized for space and not for IOPS. And those are diverging pretty quickly. Then there's IOPS-oriented SSD, written here as NVMe SSD. Those are SSDs that are getting towards 1 million IOPS per device pretty soon. Imagine a 2.5-inch disk doing 1 million IOPS. Like, that's pretty close by now. And the latencies on those are trending downwards towards 10 microseconds for those devices as well. Now, most SSDs today do something like a millisecond when you load them up with like tens of thousands of IOs. They might do 150 microseconds, but when you load them up, they go up to milliseconds. These new SSDs that are coming out, you load them up and they stand around 10 microseconds with very low concurrency. So very different performance characteristics. And then above that is NVM. And what is NVM? It's non-volatile memory. All the servers, if you follow the server roadmaps, in theory, in the next couple of years, will have large amounts of non-volatile memory in addition to DRAM. And so that means maybe 3/4 of the memory in the system would be persistent. And so it's storage. And that means that the storage stacks can take advantage of this and the apps can take directly advantage of it. And so that won't replace flash because flash still has a higher density for IOPS and capacity, specifically capacity, and we'll be supplementing. So you'll see these three things show up in the hierarchy and the software-defined storage stacks taking advantage of those as we go forward. So yeah, and so on the left here is just a rough idea of like how much of this stuff can you throw into a server. So this is your little 2U server that you're going to put software-defined storage on top of. Then how much can you fit in here? And so you can see memory and NVM. There's some debates about the ratios here. Sometimes it's a 1-to-4 ratio. Seems like it's emerging as more valid, like 1 terabyte of memory, 4 terabytes of NVM. And then NVMe SSDs, similar fairly small capacities. And you've got these super large capacity SSDs emerging up to 16 terabytes in a flash device in the next 12 months in a 2.5-inch SSD. And that's going to have much lower IOPS, but capacity. And then the magnetic storage, if you follow the trends out, you should be able to get like 0.5 petabyte just in one server. And so that'll be pushed right down if you need it. If you're really trying to build an object store, a Hadoop, or something that needs capacity, then maybe there's a reason to use magnetic storage. But the trend here is that the magnetic storage piece becomes less and less relevant for most of us over time. So if we then plonk these back on the map here and look at them, you can see the good old hard disk at 100 IOPS down the left somewhere, and flash showing up in these two domains now. So 2D NAND is IOPS flash, and so there you're getting the orders of magnitude of up to 1 million IOPS per SSD, and multiple of those in a server, but still fairly low on the capacity front. And then on the bottom left, we've got a new type of NAND. It's been around for a couple of years now, but it's really getting a focus and breaking away from 2D NAND, where NAND is basically a chip, and it's 2Ds. 2D means it's like a planar chip, and there's a lot of transistors on it. What's happened is we've slowed down the technology. We've gone from like 16 nanometers in the top left when we build flash to like 35. We've regressed the technology that does this, and then we can stack them on top of each other to increase capacity. So we've slowed it down, decreased the 2D capacity, but we can go up to 48 layers now. And so that's where these 16 terabyte SSDs are coming from, is that within a year, we should be able to see that type of density coming out, and it'll be this type of flash. And so that means that basically, for the left, 2D flash has basically replaced magnetic disk almost exclusively everywhere. And so it is more economical to buy flash for IOPS than it is to buy magnetic storage, for sure. That transition happened last year, and it's well underway. On the bottom left, it is certainly going to be true that you can get these very high capacity SSDs, so say 16 terabyte again, but that will be more expensive than a 16 terabyte magnetic disk. So if you want to, you can go all flash for the bottom right. But at the same time, magnetic disks are growing in theory to sort of 32, 48 terabyte range per disk as well. They're slowing the disks down, they're using different encoding formats, very low performance but very high capacity. So we'll see flash probably dominate almost all the things we care about, except for the extremes, which will be the capacity-oriented server architectures in the bottom left. Then the non-volatile memories. So Diablo's shown up for a little while now, actually, with a DIMM that you can plug into a system which has non-volatile memory on it. And that can either show up as a disk or memory. Actually, they just, I think they had some patents cleared in the last couple of weeks that allowed them to actually surface this as memory in the servers. And so now we're talking about being able to read and write much higher speeds and lower latencies. So you can write at about 5 microseconds, and you can read at about 90 microseconds through one of these DIMMs. Still not very high capacity, but super high IOPS. And we've been using these in vSAN in some successful configurations as well. And then a totally new type of memory, which is Intel announced server memory, non-volatile memory, which is a different physics. They haven't actually been explicit about what the physics is yet, but they've been pretty clear about what sort of the properties of that look like. So in this space, you'll see a variety of different technologies. You'll see these 3 types of NVDIMM showing up. These are the standards that have emerged already for these. At the top, you've got a DIMM. This will be like Diablo DIMM, which actually the Diablo will be the top 2, which is basically it's flash. It's a NAND flash. But you've got something buffering it, so some DRAM, and then you can read and write to it. And so some of these have a capacitor on them so that the buffer between the memory and the flash is non-volatile as well. So you cut the power off, it'll flush to the NAND as well. And so the top one shows up as memory, which means you can actually load and store to it. If you're programming to it, you can just read and write bytes from it like you would memory. And the next one down is the same form factor. It shows up as a disk. You plug it in the memory slot, but it shows up as a disk device. And this is the one we're using for vSAN now. So it has the latency properties, but it looks like a disk. And then the bottom type is the new non-volatile memory. And so that is this server memory, which is a true type of memory. It doesn't you read and write it directly with loads and stores. And theoretically, this is going to show up. There's a lot of people in the industry arranging and changing Linux, and we've done work on a hypervisor to support this. So everyone's getting ready for it, and we expect it to be there in the next 1 to 2 years. So there was an announcement from Intel on this. This is a 3D X-point, and the differences are load and store access, much denser. So cost-wise, you can expect to have a lot of this in your system, even as cheaper DRAM, because it's cheaper and it's slower, a little bit slower. It's about half the speed of DRAM, but it's non-volatile. So if your storage stack can take advantage of it, then you can use it as super low latency memory. And if you want to, you can have applications modified to talk directly to it. And so we've done the work in the hypervisor to support this. There's another talk that goes into this in a lot more detail. Okay, so then let's look at the storage solutions and see where they map. So that's basically the software-defined storage solutions are in this space. So we can see NextEnter is one example where we've just taken a single node storage stack and we've clustered it, so it doesn't scale out to super high IOPS, but it gives you all the functionality. And then you've got scale-out solutions like Scale.io and vSAN, which are block storage solutions that are meant to go after the high IOPS space. They're not aimed at super high capacity yet. And then you've got some other open source and mixed proprietary ones like Scality and CEPH. Scality is an object store. CEPH is like all-in-one file system, object store, and block storage. And those are scale out to the point where they can go to fairly high capacity. So those right-hand side, Scality and CEPH, in the orders of like 5 to 50 petabytes is some of the deployments they've had. In the bottom right-hand side, we've got Hadoop's file system, which is aimed at tens of petabytes and aimed at 50 plus gigabytes a second. And Mapr is a proprietary file system solution that operates in that space as well, that allows you to read and write as files and then run Hadoop on top of it. Okay, so what really is behind software-defined storage? And I think the easiest way to sort of edge our way into that discussion is to look at, well, what does a storage array look like today? And what is it that's so magical about it? So if you go and buy your $1 million storage array, it's this big refrigerator, and what is inside of it was basically 2 industry standard servers, and they're clustered together, and then they're connected through some sort of SAS or fiber channel multi-port switch fabric at the back end of all the disks. So that means that one server can be accessing all the disks and offering, say, block services, and then if one server fails, the other server can pick up and reattach to the disks, and so you've got hardware redundancy for mirroring, and you've got hardware redundancy for server failure. And typically at the bottom, there's order of like hundreds of disks behind it. So it's vertically scaled, not very widely. It's usually 2. And there's nothing amazingly magical, but the most valuable property about this is that you buy the whole thing from a vendor and it works. It's supported, it's guaranteed. They test all the combinations down to disk drives. Like when I was working at Sun, we used to have special firmware in the disk drives that we got the drives from Seagate and they would have bugs in them and we would fix it and we would ship out drives with new firmware. And that sort of level of testing is required if you want to have a reliable storage solution. So there's a lot of value in this because everything is tested and it's guaranteed to work. You don't want to lose your data. But really, what it is basically just industry standard hardware with an OS, fairly standard OS, and a storage stack running on top of it. So you could separate them apart. And in fact, that's actually what the companies like Nextentor have done, where you could say, well, what if I bring my own servers? I could bring my own servers and then run your own software stack on top of them. And that is software-defined storage. It is a software solution, runs on industry standard hardware, and give the freedom of different hardware behind it. So the complexity with this is that you've still got fiber channel or SAS switch backends. You've still only got 2 nodes. And so if you look through what does it take to actually make an independent software storage stack work on that, it's really hard because not all disks and SAS switches and HBAs work together. In fact, just getting that matrix right and reliable is a nightmare. And it's like a huge amount of work. And so you don't really want to be in the business of having to do that yourself. You need someone to do that for you. And so someone else has to do all that testing. It is a big investment to actually go through all those configurations and figure out what works with what. So nevertheless, this can work. And there are a bunch of different ways. There are some software appliances starting to show up in this space. So you can see things like ONTAP, there's a version for NetApp, there's an EMC one, and then Nextentor and others as well. So a better solution to that is to say, well, what if we get rid of all that complex SAS or fiber channel switches and all the compatibility with those multi-port drives and just move that stuff into the servers? And then we would have commodity servers that are very much simpler and much less to go wrong. It's lower cost because now we've just got 2 industry standard servers with maybe 24 drives in them. And the testing matrix between those servers and the drives is getting more manageable. You still need to do that because the software and the SSDs and magnetic disks all need to be tested together. Like every SSD is different. They have different error handling, different statistics that report up, different behavior when something goes wrong, different physical properties for performance. So you still need to test that matrix, but it's still simpler than the previous one. But the trick with this is it doesn't really scale out. So you're now, instead of having hundreds of drives behind, you've now got, say, 24 drives in each server. You don't have a lot of IOPS there. And so you get all the values of this, but you've sort of gone backwards in performance. So what we really need is to scale out somehow. And so the next 3 configurations will show different variants of scale out that is really the backbone for all the software-defined storage that's going on in the industry now. The first one is probably the least visible. It's emerging very rapidly, and this is not something that is a VMware product. This is an example of what's happening in the industry. There's a couple of startups doing this. There are some products around this. I would suggest it is the future of companies like Pernix Data and others that are basically building really good caching solutions. And the theory is that you just take advantage of the fact that the CPU and the low latency storage are getting closer and closer together. So if we've got servers and they've got this non-volatile memory, and that non-volatile memory is a microsecond away, then all of a sudden you've got all the performance you need. You've got millions of IOPS in that tier where the compute's running. You don't have a huge amount of capacity though, but you have millions and millions of IOPS. IOPS are free now. But you have a reliability problem because if a server fails and you cached all that stuff in NVMe, then you've lost your data. So the architectures that are emerging are basically saying, well, let's cache that top tier, so that cluster that top tier, so that you have reliability. So if I write into one server, then it gets mirrored to another server, and that way if a server fails, you've got redundancy, and then push all the cold data back to something else behind it. So that way you get capacity from whatever is at the bottom, and you get all the IOPS out of these new memory technologies at the top end. And so the examples would be either S3 or iSCSI. Both of those solutions I've seen working quite well. iSCSI, obviously, you can read and write. S3 and object stores, you'd need to convert block IOs into sequential IOs, immutable IOs that the cloud REST format is okay with. But this works, and so basically it's one different divergent track of saying SDS is basically provide all your storage solutions as really fast, inclusive cache in the compute tier, and then push all the persistence to something really slow at the back end, and you don't really care what that is as long as it scales out for capacity. So the third option here, which is of these scale-outs, would be just scale-out SDS. So this is now saying, well, that first picture we had where we separate out the software and storage, let's figure out, instead of 2 nodes, let's figure out how to make it n number of nodes and scale it out. And so it's still a pure storage platform, but now we've figured out how to build a very wide cluster. So we replicate the data across the nodes in the cluster in case of failure. We can have 1, 2, 3 replicas, maybe erasure coding. And now we get additional performance by adding nodes in the cluster. We can add capacity by getting extra nodes in the cluster. And so those software stacks, there are only a few of them that are mature enough. They're very, very complex software stacks to build because you have to build cluster systems that understand leader election, quorums, failures, what happens when you have network partitions. But if you can get all that right, then you can build a software scale-out solution. And this means that you have now outstripped the performance of those hardware arrays. Because of this solution, you can get up into many millions of IOPS. And you're using commodity servers, even though they've only got like orders of 10 disk drives in each server. You just put lots of them together. So it might be 30, it might be 100. And so this model will basically scale out storage at the bottom end, industry standard servers, some sort of storage network protocol. Something like Scale.io has its own proprietary connection to the client, and the client has a driver in Windows or VMware or whatever it is that connects, or it could be iSCSI. So you still separate out your storage and compute, but you have a scale-out storage on the compute side. So this is actually a pretty nice solution. The difference is you still have 2 silos. So you still have a storage group, and they need to partition storage, and they need to allocate it to whoever's consuming it. So let's create a data store for these VMware guys over here and put some VMs inside of that. There's still a separation of roles in that. And so that's where we get to hyperconverged. And hyperconverged is basically similar in that it's a scale-out storage solution at the back end. Understands how to have many nodes. You get high performance by scaling out. Take advantage of flash and SSD on the way through, but we've integrated it with the hypervisor so that now top-down management means there is no storage admin anymore. It's basically a hypervisor stack admin, and it has network, compute, and storage in it. And so you create a VM, and you can say, I want to give a VM with this many IOPS and this much capacity, this much reliability, and then you go figure it out. And the cluster goes in and figures it out. And so this is the simplest. Like it takes all those steps out. It's very, very easy to provision and manage from a VM point of view. And so you'll notice there's no network at the top end here. The VMs basically run on their storage. So that's turned out to be a very convenient approach, and this is obviously how vSAN works, how Nutanix works, and this is a recipe for a lot of solutions getting built on top of it. There is sometimes some question about this compute to storage ratio in this model, and in the future that can be addressed by a variety of different techniques. And as we'll see, we're starting to see some separation of the storage capacity from the servers underneath as well. So there's a couple of different ways that this capacity thing is going to change, and so we'll see that in the next couple of slides actually. The disks actually move that onto a storage network behind, and so the nodes, the hyperconverged nodes can be separated from the capacity, and then that allows you a variable ratio. Okay, so on that note, let's talk a little bit about the interconnects. We don't have much time to go into too much detail here on those, but on the interconnect side, there's a bunch of changes going on that are important that allow some of that to happen. And I just want to talk through this model. We just basically think of the compute on the left-hand side. Maybe it's hyperconverged. Then there's a fabric, and I think that's the key term. There's a fabric that connects the compute to the storage. And today that's fiber channel, or mostly fiber channel. But the new one is NVMe over fabrics. And then that's either connecting you to an array in your data center, or it might be a scale-out storage. In scale-out storage, there'll be adapters, like HCA adapters, and then something like SATA or SAS or something to the drives at the back end. So just keep that in mind as we walk through this. Fiber channel is evolving pretty quickly, so that would be the fabric in the middle is fiber channel. And so it's accelerating in speed, but still very limited in its capabilities, functionality for administration and other things. And so it's up to 32 gigs now, and we're heading to faster speeds soon. But at the same time, the network speeds are going much faster than that. So we would see Ethernet. It seems like the 25 gig Ethernet is becoming very much a commodity and very good price point, actually. So a lot of the switches are actually getting to that point where the 25 gig price point is going to be what we see in volume. And then you can do 4 of those and get 100 gigs in one Ethernet port. So I think we're actually going to finally see, due to maybe the NVMe work, Ethernet being used as a storage fabric. Now, it certainly is at the back end with things like vSAN, because the internode traffic is all going over Ethernet. But from the client application to the storage as well, NVMe over fabrics looks like it's actually going to offer enough value that some of the other protocols like iSCSI and RDMA over Ethernet, where they've tried to do this in the past, NVMe over fabrics has a good chance of actually converging the two together. So the network's far outstripping anything else, and there's definitely going to be enough network speed to do this, and the new protocols are actually going to be the thing that fills out the rest of the story. So we'll come back to the fabric piece. So just at the back end, there's an interesting story here. Basically, the back end and the fabric are converging as far as the protocols. And the back end is basically, here's our server, and we want to plug some disks into it. It used to be that we had a server, and we plugged our LSI logic or whatever else card inside of it, and that had SAS coming out the back end of it, and we'd plug some drives in the front of the machine. And that was SATA for the low end, SAS for the medium to high end. And so that had some limitations. That card is pretty expensive. And on the way, by the way, that card's getting less and less relevant because that card used to do things like RAID and other special redundancy. None of that's required anymore because we're doing that in the software-defined storage layer. So redundancy is across the network, across hosts, rather than in the card. So the card's basically becoming a glorified interconnect mechanism for the disks. But it's also slow. So SATA and SAS is a pretty slow protocol. We're getting to SAS 12 gigs, which is like faster than it had been. But what's happening to get around the slowness, people started finding that their NVMe or their SSD cards were much faster. So just put it on basically, put the whole thing on a card and plug it in the PCI bus. And now we can all of a sudden get up to 4 gigabytes a second instead of like most of the SSDs, which were tapped to like 500. And so that was there for a little while, but then the standards have come around. It's like, well, wait a minute, let's make that a standard. And so that became NVMe, which is different to the term we used earlier, like non-volatile memory. This is NVMe is a standard for disk drives and flash cards. And so that became now is a standard protocol. So you plug your card in, you get faster speed. But now what's happened is the server vendors have said, oh, wait a minute. So that SAS connector, there's some spare pins on it. So let's bring the PCI bus all the way out to the disk drive slots at the front of the machine. And so that NVMe protocol is now part of the same connector that the drives plug into. So you'll notice on some of the new Intel and Dell machines, or EMC machines, you can take some of the slots are different colors, and those are NVMe slots. And so those drive slots go at like 4 times the speed because they have this NVMe coming all the way out. And what that means is on this right-hand side, what is the role of that card now? It's basically just a bunch of wires. There's no logic on it. It's not a host bus adapter anymore. The drive plugs straight onto the bus. And so over the next few years, we'll see the extinction of the HCA because the drives are all just talking natively to PCI Express, and they're all doing NVMe. So that's a big change because like a lot of our testing and configuration of our servers and everything is all around like which HCA do I use and which software supports that, but that will change pretty quickly. Okay, so fabrics, very quickly. So we've got fabrics which are iSCSI and fiber channel. We've seen those in the past, we know what those are. But the new one is NVMe. And so that same protocol that connects the drive in the front of the machine onto the PCI bus, that has a bunch of upper-level components to it. And it's basically the industry's looked at SCSI, they've looked at VVols, they've looked at a fiber channel, and thought about very carefully what do we want in a storage stack in the future and what don't we want. And so this NVMe has evolved into a storage stack and protocol which looks like it's going to replace SCSI. And the interesting thing is the upper end of NVMe is a storage access, like the device driver that comes out of Linux or Windows. It looks exactly the same whether you're just talking to a local flash disk in your machine. But now we've got NVMe fabrics, which means that you can talk over the network. So I'm going to go forward a couple of slides. So you can talk over the network. So there's an NVMe core that talks over either PCI Express, or it can go over RDMA over InfiniBand or Ethernet and then talk to something at the other end. And so you have one storage stack which is aimed at being universal. It could talk to a DSSD box or something else on the network, or it could talk to a local SSD, and it's just one device driver. And by the way, its latency of that stack, because it eliminates 70% of SCSI, is much, much lower. So now that we can actually talk to these devices in the order of like 10 microseconds instead of the old heavyweight SCSI stack that was there. And you can see here, actually, here's some devices that are being accessed at 8 microseconds across the Ethernet. So we're doing random writes across the network to these devices. So a new stack's emerging very quickly and will replace the existing stack, in my opinion. So, okay, so the other thing that's changing is that the disk drives are inside the machine. Like we took them out and we put them in the machine. We took them away from SAS and put them inside the machine. And now, because of the in the rack fabrics, we've got over Ethernet, we've got PCI Express. That means that if we want to, we can move the drives or share the drives across the rack cluster. And it's fairly early days for this, but it's possible. But I think this is the area that the hardware's doing it, the software's not quite yet there yet, and we'll see some emergence. So what it would look like is here's a rack, and here's a logical configuration of this. Here's a rack, here's all the compute blades, and here's all the storage boxes with all the drives in them. And there's a network in the middle, and it could either be Ethernet with RDMA, or it could be PCI Express, and everything can see everything. So that way, if the storage architecture is written the right way, then when something happens like a host fails, you can still see all the disks. So you don't have to copy all the disks, all the data onto a new machine. And you can have a variable compute to storage ratio. So this is where hyperconverged and this architecture meet, and you get the best of both worlds. Like I said, early days, there's a couple of examples like Dell or EMC have a machine that does this already. It's not really being used by any of the software stacks, to my knowledge, but it can already do this. And so the hardware exists, but the software sort of playing catch up at this point in time. Okay, so this is like my little prediction, which is I think that if this pans out, the speed it's moving pretty fast, which means that for storage standards in the next few years, we'll start to see more adoption of this. SAS and SATA certainly already have moved to NVMe, but the chances are that iSCSI and Fibre Channel also move to NVMe over fabrics. And watch this space, but it's moving in all the right directions to say that there's a pretty good chance it's going to happen fairly quickly. Not in like 12 months, but it's worthwhile starting to pay attention to it. Okay, I think we've covered that. So the last part, we'll do this last couple of slides, just bring it back together, and then we can do some questions and answers. But so what about this? So far we've talked mostly about block storage. We've talked about SDS, and it's replacing our SAN, and it's giving us higher IOPS. But what about all those other storage protocols that are out there, the storage services that things like the cloud native apps needed, and even in the enterprise? And there's a ton of them, right? These are all storage services. So if we think of a data service as something that consumes persistence and gives you a service over the network, it could be an iSCSI server. There you go, it's a data service. We don't know what's behind it, but it's giving me a read and write block protocol. You can argue that a SQL database, like an Oracle, is a data service too, because it's just giving you a SQL protocol on the front end, and it's running somewhere, and I don't really know what's behind it, but it's giving my persistence, and SQL is the protocol I use. Likewise, you've got things like Cassandra, MongoDB. Those are data services as well. They want to persist data somewhere and manage it, but again, the instances are runtimes instances of those applications. But what they're exporting to the application, the thing that the cloud native apps or container would consume, or even a VM, would be that data service running. So we've got S3 as well. So think about an object store. We should be able to run an object store on whatever platform this is. And so if it was Ceph or Swift, then I could say, here's my S3 protocol with REST, and I can read and write those objects into it. And so from a developer point of view, again, they're just seeing a data service. So what we're seeing is this emerging pattern, network, and on the network, we've got all these different protocols at the front end. And the back end, we need to host all these different services. And what we don't want to do is end up running each of those as a silo. So this is actually how it's emerged today, even in the big cloud companies. Like I went to Twitter and spoke to a few people there, and they said, oh yeah, we have like our Hadoop cluster and our stateless runtime cluster, and we have our Manhattan cluster for key value, we have object storage, and they're all separately managed things with separately managed teams, different types of networks, and the machines they order are different. Like those compatibility lists of which servers work with what. Each team gets to choose which server they want. And sort of like the opposite of where we were with virtualization. We've got all these silos and everyone arguing that it's special because it's data and like therefore you can't do consolidation or have a universal platform. But a lot of people are noticing this and realizing that there has to be a better way to get to a common platform. And so in these last two slides, this is the two options that the industry has on that I see is how to accommodate this space. And the first one is talked up a lot. Like I've seen a couple of even big companies actually come and say, this is our strategy. We have this universal data platform, and it's going to have iSCSI and block, and it's going to have an object store in it. And by the way, it's got a key value store, and it's got some Hadoop support on it as well. So it's everything. Like you don't need anything else. It's one-stop shopping. And you look at it and say, okay, I can sort of buy it when it's going to be an object store, and then maybe block converged. But when you start telling me that you've got a key value store, I'm going to start asking you, how do you index it? What's the developer community? What's the way that you access this key value store? And are you really going to be able to compete with someone like MongoDB, who's totally focused on that industry? And have like won over the developers and like got a very large investment in what that key value store is? Like, no. Like, you're just going to be like 1/100th of what that thing is. So if you try and consolidate too much, you end up with a compromise on a lot of these other things. And so this is why I put a couple of unicorns on here, because I just don't think this exists. I don't think you can get there. Like you do it, and it works really good on marketing slides, but it's not really that valuable in the real world. But the thing you're trying to go after is good, though, which is one HCL, one set of cluster nodes at the bottom of it, because that dramatically simplifies your world. That's where you want to get to. So the other option, and my personal belief on how this is going to shake out, is that you still need to get to one HCL, because having seen the investment that Microsoft and my experience at Sun and what VMware had to put in with vSAN, it's a monumental investment to get software working compatibly with storage hardware. And the testing and money that has to go in, the partner relationships that has to go into that is huge. So to do that twice or three times, or try and do that yourself as an enterprise customer or a service provider, it's a lot of work. And so what you want is someone else to do that for you. So someone else does the HCL, all that testing, and provides you a platform which is almost at hypervisor level to get access to all that storage, and then surfaces up a set of APIs and runtime environments which is sufficient to be able to run all these data services. So when we come back to things like Hadoop or CEPH or MongoDB or MySQL, they're just data services. What are they? They're probably VMs or containers, and they themselves require a certain amount of SSD for their log. Maybe they want some replication. In the CEPH case, they don't want replication because they're going to replicate at the data level. And there's all these APIs that need to be set up. They want to be arranged in fault domains so that if it's Cassandra, Cassandra knows it's already replicating. It knows that it can lose a node, and it's partitioned itself so it can survive that failure. So there's a bunch of API things that need to happen in this platform. So that platform would need to not only have the HCL, but it would need to have a runtime set of APIs that give you those properties of failure domains and has a scheduler and a placement algorithm and everything else inside of it, and then lets you run those instances. So my money's on this architecture showing up. And there are some entry-level versions of this being done already today with different platforms. And we've been experimenting with this with vSAN, putting a lot of effort into thinking about how that would work for those new applications. And today we've got block storage and Hadoop running on the same platform. And we can do that through some policy controls on vSAN. But the rest of them, like, there's new work that would need to be put in, new APIs and so forth. So yeah, this is my bet on where I think that's going to go. So yeah, if we think about that, then what does that mean as software developers or SDS? So some of you might be developers of SDS. Some of you may be consumers. But if you're a developer of SDS, then these are the opportunities that could be there. So how do we have the right APIs, the right placement groups, and everything else in the platform the way through? So on that note, yeah, so that's my thoughts on what's happening with the SDS platform. And I think if we can get to that point of convergence, then we'll actually have achieved the same thing for storage that we have for compute. Thank you very much. So I was reminded to remind you to fill out your survey. And if you've got any questions, I guess we've got another 10 minutes, and I'm more than happy to use that time if there are any questions in the audience. I think there's some microphones as well. Or if not, just find me afterwards. I have no slides. Why is that?
What's the storage?
Yeah. Someone quickly fail over. Do we know why that is? Thank you. All right, that's better. We could do the whole talk on just one slide and see how that goes.